Hello, good morning. Yeah? Good morning, everybody. Thanks for coming to this Severo Ochoa colloquium that Dr. Laurence Sabin is going to give to the audience today. Dr. Sabin got her degree in Guadeloupe, in the Université des Antilles Guyane, in France, but at the other side of the Atlantic Ocean, in physics and chemistry, and she got a master at the Université de Nice, Sophia Antipolis, in continental France already, in astronomy. And she started her PhD under supervision of Professor Albert Sigelstra in Jodrell Bank Center for Astrophysics in the University of Manchester in 2004. Her PhD thesis was about the study of planetary nebulae and magnetism using the survey IPHAS, which means Isaac Newton Telescope IPHAS Survey. Then she got a Marie Curie fellowship for the program ERA, Early Stage Training in Astrophysics, and she continued her PhD at the IAC in Canary Islands in Tenerife under supervision of Drs. Corradi and Mampasso. Dr. Sabin got her PhD thesis in 2008 in Jodrell Bank Center for Astrophysics in Manchester. She got her first PhD in 2010 in UNAM in Ensenada, where she's leading projects on evolved objects and about magnetism for stellar and nebular objects. Her second postdoc was in 2012 in the Instituto de Astronomía y Meteorología in Guadalajara, Mexico, about cinematics and polarization in evolved stars. She got then a professorship, a contract in the UNAM in Ensenada for young researchers in 2015 and finally confirmed in 2010. From that time, she's member of the Consejo Interno del Instituto de Astronomía, that I don't know how to translate it to English, internal council of whatever, as a representative of the researchers in the location in Ensenada, and she's also part of the Comité Académico de Ensenada. Dr. Sabin, that in Spanish I guess that everybody calls Sabin, right? Is member with a level SNI 1 since 2012, and now she is investigadora titular A, so A, full-time from very recently, 1 month or one and a half months ago. About her research, she has been working in the IPHAS survey and in the first detection of surface magnetic fields in post-AGB stars, as the cases of U Monocerotis and Ars Scuti, where they detected for the first time those magnetic fields in post-AGB stars. It's also to notice her work on her collaboration, her contribution in the work published in Nature Astronomy about the inside-out planetary nebula around the Born Again star that Martin showed us several months ago. Among other things, important contribution in her CV, she has been contributing to the formation and education of students in the Universidad de Guadalajara, Universidad Iberoamericana, and she has been participating in the development and operation of a new polarimeter at the San Pedro Martyr Observatory, which is called with such nice names that we love to put to the instruments, is FICUS, Fiber Coupled Unit System. She's also a member of the project Saint X, which is a 1-meter telescope in the in San Pedro Martyr Observatory for the research and follow-up of exoplanets, of the Earth-like exoplanets around orbiting ultra-cool stars. And today she is going to talk about her main fields of research. So very welcome, Laurence.
Thank you very much. Thank you for having me here today. So I've been asked by Martin to talk to you about what I've been doing for a long time on a survey on detecting objects in surveys, because I know that you're working here on a survey called IPHAS. So I will actually share with you what we've been doing in IPHAS and what are the pros, what are the cons, what are the things you have to worry about, etc. So first, I'm going to go in the galactic plane. So everybody knows the galactic plane is hosting a lot of different kind of objects. So we have star-forming region, massive star remains, the remnant supernova. So basically, a lot of the mass, if not most of the mass of the galaxy is concentrated here. So we have a large amount of gas, we have a large amount of dust, which means that we have a lot of extinction in that place. So if you want to find some objects, if you want to do a real census, so it's going to be more difficult. So we're going to work as an example for the case of the planetary nebulae, so the detection of planetary nebulae. So what are planetary nebulae? So because Martin is working here, so I guess that you already know what are the kind of object they are. So basically they are shell of ionized gas which are surrounding evolved intermediate, low and intermediate mass stars, basically between 0.8 and 8 solar masses. So those are really old object, ancient object. So the importance of planetary nebulae in the galaxy, and in fact in most of the galaxy where you can find them, it's basically is the refurbishment of the galaxy in different kind of material. So you have different type of elements, different type of dust. So basically the main thing that we can say about planetary nebulae is that they are objects which are, as I quoted here, an incredible plasma laboratory, because in those small objects, well, small, between quotes, so you have lots of processes going on. So you have photoionization, recombination, you have shocks, you have the effect of the central stars, you have cooling, you have magnetisms, you have the effect of binarity, you have all the internal dynamics, etc. And all those, you can study it at all the wavelengths from X-ray to radio. And it happens in objects with a very short lifetime, between 10 and 20,000 years. So those objects are really, really interesting for the evolution of the galaxy. And of course, because they look nice. So you have a very beautiful planetary nebulae with different kind of shapes that we try to understand using all the processes that I already talked about. So, how many planetary there is in the galaxy? We know that they are important, but we need to know how many there are. We need to know if there are an abundance gradient based on how they are distributed in the galaxy, if they are so important to enrich the galaxy in chemical elements. Is there a space density, a scale 8? What is the birth rate of planetary nebulae, the total one? Do we have a preferential distribution of the galaxy? For example, based on their morphology, do we find more bipolar at some places, more round at other places, for example? Talking about morphology, most of the studies that have been made stated that we have a dominant bipolar morphology, at least in all the places that have been surveyed. So all those questions require statistics, require a good census. The problem is that, of course, and it's normal, everything we've been doing, well, it's with what we have, and what we have is the easiest way to detect planetary nebulae, which means we have only the bright one or those with an intermediate surface brightness. So basically, we are biased against everything which is faint. So those are not entering in those statistics. So we won't be able to fully answer all those questions until we have a at least the most complete as possible statistics. So let's talk about those who are missing. So David Frew, in his thesis in 2008, calculated that we should find around 24,000 planetary nebulae, more or less, plus or minus 4,000. So far we only know 3,500, and including the one that I will talk to you about today. So there's a lot of them that we are missing. Who are they? So basically, I don't know if you can see it here. If you don't see it, it's good, because actually this is why we don't have them in our census. So we have, for example, the planetary nebulae, which are hidden in the interstellar medium, due, of course, to that extinction that I talked to you about. We have the old planetary nebulae. We are starting to disseminate in the interstellar medium, so they have a very low surface brightness. But we have also planetary nebulae that are probably bright, but they are located in regions that are not that studied, like, for example, the anticenter, the galactic anticenter. We have the distant, the very distant planetary nebulae, which are really compact, and sometimes they are overlooked in a lot of senses. And we have the planetary nebulae, the small planetary nebulae, which are within a lot of other stars that are in an enclosed area in the galactic plane, for instance, and that also are overlooked. So all those may account for all the planetary nebulae that we are not seeing, and that's why we are never not reaching 5,000 known planetary nebulae, for example. So what we need to do, we need to find them. So are we going to find them? So we need to have a tracer. So we're going to use the H-alpha emission. Why the H-alpha emission? Because it's going to trace all the ionized objects that we can find at the beginning and at the end of stellar evolution. And a lot of short-lived objects, for example, would show H-alpha emission. So we can differentiate them in two, for example, the young object like Tetori, Abigaro, or H2 region, or evolve like planetary nebulae, post-AGB, Wolf-free star, symbiotic nebulae, etc. So we're going to use that H-alpha as a tracer to detect our planetary nebulae. What has been done before? So, of course, we are not the first one in doing that. There have been a lot of other surveys before, so here I quoted only 4 of them. So you have the SSH, for example, which was done in the southern hemisphere. So you can see the coverage in declination and in galactic, also in galactic coordinates. So the technique, the most important thing is the technique and the spatial resolution. So as you can see for the SSH, it was done with photographic plates. Good resolution, 0.67 arcsegons, but the technique was, well, that was what they had at the time. So we can do better. If we skip at SESHA and VTSS, those two were done with CCD camera, so we are in improvement from the photometric plate, but if you look at the spatial resolution, it was not that great either, because it's only at the arc minutes resolution. So what we need a survey, a new survey, tracing, allowing us to detect all those planetary nebulae, for instance. That means that will trace H-alpha with a good resolution, with a good and with a good coverage as well. So here's come IPHAS. So as was said, so IPHAS stands for Isaac Newton Telescope Photometric Halpha Survey. So as it names, means the survey was done with the INT that I show an image here, which is a 2.5 meter telescope. So it's a fully photometric CCD survey that started in 2003 under the leadership of Janet Drew at UCL. It's a wide field, the INT, with the INT we're using the wide field camera, so we have a 0.3 square degree field of view. Important things, the pixel scale, here, 0.33 arcsegon per pixel. So we have a much better resolution than what has been done before. So I'm skipping those. The area was between latitude between 5 and -5 degrees. above the plane, and we were able to scan 1,800 square degrees of sky. To do that, so we had to observe a lot. So that was done between 2003 and 2008, where we had at least one pointing. But practically the service ended like much later, like 2013, 2014. That means that we had reobserved all the areas that were where we had a bad seeing or any area where we had problems. So that was reobserved. So it took quite a long time. And the seeing at the place was, the median seeing was 1.1 arcseconds. And the photometric calibration was uniform in the Vega system. So we had already two relays for all those data. So we have the Gonzalez Solaris in 2008 and the one from Barentsen in 2014, which is the one where you can find all those data for the photometric. Please. Oh, oops. Okay, just to show you here. So you have all in black, so you have all the places that have been observed with IPHAS, and importantly that I say the galactic anticenter that we are covering here. For the little story, the galactic anticenter is a very difficult place to observe because, well, it's around 6-7 hours in right ascension, and generally you observe that during winter time in the Canary Islands. So we generally have, well, the probability of having a bad weather are higher at that time. So that's why we had to observe quite a lot in that region. So the filters, important. So we observe in three filters, H-alpha, Sloan R, and I. The H-alpha got FWA shame of 95 angstrom. So basically it's H-alpha plus N2. And the nitrogen 2 line at 6584 angstrom. We observe in 120 arcsegon in H-alpha, 30 in R, and 10 in I. So here on the side, I'm showing you three images of an object, which is a planetary nebulae, a new planetary nebulae that was found. So you have the R image, the I, and the very important, the higher flux that you have in H-alpha. So the depth, how deep are we going? We can detect those objects. For point source object, we can go in R from 13 to 20 magnitudes. For the extended emission, which is the one we are interested today, we can go down to 2 times 10 to the minus 17 ergs per centimeter square second arcsegon square in H-alpha surface brightness. So we can go pretty deep. And finally, the nomenclature. So if you go in Vizier or any other catalogs, so you will find the compact objects named as IPHAS, J and the coordinates. And if you go for extended object, it's going to be IPHAS X, J, and all those long numbers. So on the side you can see the different filter that we are using and how broad they are. We have a IPHAS nebulae group. Actually, there's plenty of different groups in the IPHAS consortium. So our group was formerly known as the B group. So what we want to do is a systematic search for planetary nebulae, but not only planetary nebulae. We want also other type of nebulae like remnant supernova remnants, so H2 regions, large symbiotic star, for example. In the northern galactic plane, we are looking for either compact and extended nebulae, and we're going to use two methods. One is the photometry, and the other one, the mosaics. So let's start with the photometry. So basically, we use photometry, of course, for the most compact or point source objects. So we are using, in the catalog, basically you have a tool that allows you to pick up all those, to select all those objects. So if it can detect, according to the size of the object, if it can detect them as point source, so they can be selected that way. If not, they will be discarded. So basically what you're using are color diagram, and Corradi et al. And Vironen, and Corradi in 2008, he was looking for symbiotic stars, and Vironen in 2009 was looking for planetary nebulae. So they used those type of diagram, color R minus H alpha, R minus I. Of course, while they don't use it alone, they also use, in addition, to mass data of the same targets, so they can have a better constraint on the detection of those objects. And you can see, for example, where stand in the red dot are the S-type symbiotics. So you have the planetary nebulae, which are here on the corner. So you can discriminate basically different type of population. And for example, you have the green dots, which are where you have cataclysmic variable, for example. And you can compare that to what you have in the two-mass color diagram, and then you can constrain where are your planetary nebulae. So this is the way that this is the tool that they use to detect those symbiotic stars and those candidate planetary nebulae. I will talk about what I've been doing, basically, is using mosaics, because I was looking for extended nebulae, those that the photometric catalog was discarded because they were not point source. So to look at those objects, what we did was creating 2 degrees squared H alpha minus R, that's been continuum removed mosaics, using all the different frames that we obtain from the survey. And we use different type of constraints that are in the table on the side. We have constraint on the sky level, on the seeing, on the limiting magnitude, etc. So basically, if an image was not fitting within those constraints, so that image was discarded, and if we have, because we are observing several times, so that could be replaced by something else, by another image, sorry. So the most important thing here is that, the binning. So we use 2 types of binning of 15 and 5 pixels. And I will tell you in a minute why we did that. Using the mosaics, the detection mode is not using a color diagram, etc. Is the old visual search for nebulae. So we produced a bit more of 1,500 mosaics in total. Why we need binning? So depending on the binning technique, depending of how large is your binning, you will be able to detect different type of objects. For example, the 15, we use a 15 by 15 pixels binning. Basically, it's 5 arcsecond binning. 1 pixel is 5 arcsecond on the sky. I remind you that the original one is 1 pixel is 0.33 arcsecond. This is the image that you have. But we degrade those images such as to have 1 pixel, which represent 5 arcseconds on the sky. So we are losing resolution, but at that point it doesn't really matter for us, because what we're looking for really low surface brightness objects. So we are trying to bring them up from above the sky limit. So and also, if you have, you can look at the contour or the shape of other nebulae that can also come up from the images. So the degradation here is in resolution is not problematic if you're looking for very large objects which are very faint. We use another one, another binning at 5 pixels binning. That's mean in that case that 1 pixel is 1.7 arcseconds in the sky. So basically it's, we use that to detect intermediate size nebulae. Sorry. So those nebulae, they were too small to be picked up in the first one, because in the first one they were just like small dots, like stars. But they were too large to be picked up by the photometry, because the photometry says that they are not point source. So we had a gap here, so that can be solved using those intermediate binning of 5 pixels. So here I'm showing you one type of one mosaic. So it is all that region. So from there, you can see clearly this one, this object here, which is NGC 6888. But I guess that you cannot see what the number here at 3 there or at 2 here. So you have to look all your mosaics, and then you can see that in, for example, at the number 2, what you have is that nice bubble here that you wouldn't have been able to pick up otherwise. Okay? So this is what we have been doing for most of the, for all the sky. The mosaic is efficient if you want to detect low surface brightness objects or intermediate size objects, but there are some problems, of course. So for example, if you have a problem, if you have the difference in the sky background between the H alpha and the R image, because I remind you that it's a H alpha minus R, those are H alpha minus R mosaics, so you can have also some issues. So we produce confidence maps with the data on the bad images to look, to really pinpoint where those what those bad images were. You have artifacts, there's a lot of artifacts due to the CCD ages, the reflection on the CCD age, and due to the seeing difference, for example. So a nice way to see if an object that you picked up in a mosaic is an artifact or not, you go to the original one at the nominal resolution, and because it's observed most of the fields are observed several times, then if your artifact only occur, your artifact actually will only occur once in all your frame. So if this is not something which is consistent, so it's not an object, it's something else. So we have the bad images, which are due to the weather condition, but generally when there's weather condition, we observe again those fields. And for the storage, you have the weight of those mosaics. This is also one of the constraints that we had when we created them, because of course, having all those mosaics can be really, you have to find a way, or better said, you have to find a place where to put them. For example, the 15 pixels mosaics, each of them are 20 megabytes, and the 5 pixels mosaic, each of them has 135 megabytes, and you have more than 1,000 of each. So it can be a problem, but all those were hosted in Cambridge, in their Cambridge database. So on the side, I'm showing you some type of artifacts. So here, probably you're not seeing really well here because it's pretty faint, but you have something pretty roundish here. In a 15 by 15, 15 pixels mosaic, that will appear as a genuine nebulae. And then you have to go back to the original one to check if it's an artifact or not. You have those, we have those which are reflections. Here again a reflection that you have that trail, so this is also an artifact, and you have those small here and here which are also that different type of artifacts. So those are the most common artifacts that you will find in your mosaics that you will pick up anyway, but it's in the second run when you're studying all the objects that you selected that you will see if they are artifacts or not. So in that case, using that method, there's no other way. So the first catalog that we had was in the 18-20 hours region, which is near the galactic center. So those results are for the inspection of the 15 pixel beam mosaics only. And basically, when it comes to planetary nebulae, we find 100 known nebulae in that area, and we had 233 candidates extended nebulae. So in all the area from 18 hours to 6 more or less hours, that means for the galactic center, the galactic center, we had a total of like 3,000, between 3,000 and 4,000 objects that were detected. And it's only for the first pass. That means that if you go again and look at the mosaic, you will probably find something else, something new. So here are examples of nebulae that were found, that are genuine nebulae. So we have this nice one, which are basically, you can see two, like a kind of bipolar. You have two parallel trails. You have that roundish, like nearly basketball-like nebulae, and you have that nice round nebulae. So all those were detected thanks to the binning, the eye binning, and they could be able to emerge from the background. Another example here, you have this arc here. And IPHAS is pretty efficient for a type of planetary nebulae, which are the planetary nebulae with interaction with the interstellar medium. So basically, those are going inside the interstellar medium, and the only thing that you will see is the bow shock. That means where you have the compression with this interstellar medium. So most of the nebulae is either really have a really low surface brightness or is already gone, actually. And on this side, you have, again, another type of nebulae. So here, the binning is it's a 5 arcsagon again. So you can see that for that one, we were able to see some filaments. And all those things, you would not have been able to see them using only the 0.33 pixels images, that means the original images. You need the binning technique to detect them. Once you have selected all your objects, because we only have those 3 filters, we were not able to differentiate what is what. If it's a planetary nebulae, if it's an H2 region, if it's symbiotic, because they all have the same type of light, the same type of emission. So you have to do spectroscopy. But because our objects are so faint, you have to go for big telescopes. So some of them, we were able to observe them with 2 meter class or 1.9 2 meter class telescope, but a lot of them, we needed 10 meter telescope. For example, we use the GTC a lot to do the spectroscopic identification. And even with the GTC, sometimes you only have like 6 or 7 lines, emission lines. But the lines that are needed to distinguish what kind of object they are. So we released the first catalog, and where we find 159 true, likely, and possible planetary nebulae. So the likely and possible shows you generally how faint they are. They are so faint that there's not that many lines, there's not that many hints on if they are really planetary nebulae or they can be something else. So you would need some other type of analysis to really confirm them or not. So we also conducted deep imaging for the morphology, and here are some different objects, and I will draw your attention on that one, for example. You might not see it right here, but above this, what appears to be oval, elliptical emission, there's 2 nice lobes, but they are so faint that you need even more observing time to be able to see them. But this is just to show you that those lobes appears really well if you bin your images. So this is just to show you, again, to underline the faintness of those objects and why they have been overlooked in all the other senses, and why you have those problems when you're doing statistics of planetary nebulae. So just a quick results. So here is the distribution of our IPHAS object. The IPHAS objects are the black dots compared to other planetary nebulae that are already known. So generally the white one are those from the Strasbourg catalogs, which are generally brighter objects. So this is the distribution in latitude and in longitude. So we are basically seeing all our objects, of course, between the -5 and 5, which is the IPHAS boundaries. So here is the distribution in terms of sizes. So we have a peak for objects with size around 15-20 arcsegons, but we can see that we have a large span up to 400 arcsegons in size. So those ones, so we can pick up really large and really faint and really evolved objects. In terms of morphology, so we differentiate them in elliptical, round, bipolar, irregular, asymmetric, or quasi-stellar objects. So as you can see, we found, for example, 45 bipolar, 45 round PN. And it's interesting because we always assume that we should find more bipolar objects lower on the plane. And here we find a lot of round planetary nebulae. And the round planetary nebulae is a population that is generally missing because round planetary nebulae are generally assumed to have a lower surface brightness. So maybe we will be able to revert that assumption that there's more elliptical or more bipolar lower on the sky. Maybe the round population is not really fully represented, and we're contributing here by increasing the number of this morphological type. And we're doing also follow-up analysis. So we're not only detecting them and doing the spectroscopy to see what they are, we're also doing some follow-up. So here is an article by Ramos Larios in 2017 where we looked for the H2 emission of those objects and to see how the H2 emission in those was comparable to those of bipolar planetary nebulae that were already known, for instance. The follow-up includes spectroscopy for the identification, deep optical imaging, multi-wavelengths and multi-technique analysis, and also we tried to look for the central stars. Except we not only have IPHAS, we have also UVEX. UVEX is the blue counterpart of IPHAS on the same area. So what you can do with the blue side, particularly the U band, you can look for the central star of those objects. So on the top, I'm just showing you one of the objects, which is called the necklace, just to talk about the deep imaging. So this is an object that was discovered in IPHAS and that was observed with the HST. So you have a better look at what we call the necklace, this necklace of knots around the central star. And here you have two PN that appear in green, but they're really, really faint. And in blue, I hope that you can see, because it's actually also faint, you have, using UVEX, we were able to detect the central star of those objects. So the combination of surveys with the same characteristic instead of depth, instead of pixels size, allow you to combine them and to be able to have a full analysis of those extended planetary nebulae. I talk a lot about planetary nebulae because this is what I'm doing, but we'll detect also a lot of different types of objects. For example, we detect new remnant supernova. We detect 5 new ones that were also overlooked because in that case, not because they were very big, but because they were small. So we detected rather smaller new supernova remnants that are added to the general catalog of supernova remnant by Green. So basically, here in that field also they have a problem of, they have a census problem. So they say that you're supposed to be able to detect 1,000 supernova remnants in the galaxy, and included those 5 new that we added to the catalog. There's only, last time I checked, 295 of them detected. So here again, we have a problem of detection. We have a bias in the census. So of course, we detect those objects. We are doing the spectroscopy. We have them in a new diagnostic diagram that allow us to confirm their nature. We also detected nova. For instance, so this is an article by Martin and also by Santa Maria, those two in 2018, where we had that object that we classify as first as planetary nebulae, as probable planetary nebulae. Then we look at it a bit deeper, and what we could see that it looks a bit another nova. The shell, at least, was looking like another known nova. So we did the observation to identify the nebulae, but also we observed and we analyzed the central star. We were able to detect the period. We were able to have the kinematics of the whole structure, and we had our first IPHAS nova extended object, if we're talking about the shell, because there's not a lot of them, a lot of nova that show an actual shell. Can we do better? So I'm going to talk to finish about the visual search, the RGB imaging, and machine learning to help improving the detection of those objects. So the visual search, the con, it's long. Well, it was all my PhD. So it's a very long time to look at all those mosaics. It can be painstaking, but the pro is that by experience, there's nothing better than your brain to detect objects, even the faint one. That means that with time, your brain will separate artifacts from true objects, and you will even have the intuition of what pattern will be likely planetary nebulae or H2 region, etc., etc. So your brain will adapt, and you can detect all those filaments, etc. Of course, it's getting easier with time. So if you have a 3 years PhD, then you have time to get accustomed to that. But it's painstaking. Then you have the RGB search. Basically, what we're doing, we're using composite mosaics. So we have the H alpha minus R, but you have also the H alpha of the quotient, H alpha divided by R, and another one that can be the H alpha one, just to have a third frame. And this, we use that to detect intermediate size nebulae. So when we combine all those type of mosaics, the H alpha minus R, the H alpha divided by R, and the H alpha, you affect a color to each of them, then you can, the nebulae or the compact nebulae, the intermediate size nebulae, basically are popping up as a really characteristic color. So it's easier to pinpoint. But again, it can be quicker than what you can do only by analyzing one type of mosaics. The problem is that, of course, you have, it won't discriminate against artifacts, etc. You will pick up the artifacts. You will discard them later, but at first instance, you will pick up those artifacts, and it's still a visual analysis. So there's no other way. So that method was used, for example, by Mizalski et al. When they were looking for objects in the south in the MASH survey, actually. The next level, which is more recent, is machine learning. So basically, the pro is that it's automatic, it should be quicker. Once you train your network, So according to a pattern, I will talk about that in the next slide. So you should be able to pick up all the objects that you want. The con is the way you produce your mosaics, because if there's plenty of artifacts, you will have also to train your network to find those artifacts actually and to separate them. So this is something that will totally depend on the quality on the images that you have. So to do that, you need neat images to have that, and also you have to take care of the reliability. That means that we discussed about that yesterday, and that probably we would lose a percentage of objects. But if after doing that you're losing like 50% of those, well, it's not, doesn't really compete well with visual inspection. So, but it's all about training. So with IPHAS, what can we do? So remember that we only have the H-alpha, R, and I filter. I say that because I'm comparing, for example, with JPAS that will have much more filters, so it will be easier. So in our case, with those 3 filters, what we can do is using our AGB images or AGB techniques, and we could train our network, but it's going to be a binary indicator. So basically, your network will tell you it's a nebulae or it's not a nebulae. It will pick everything based on the color that you have, on the pattern of the patterns that you have. So it's just going to be one, it is or it is not. And you will have, again, to go back to the selection and to have the everything which is spectroscopic analysis, etc., to determine what kind of object it is. So the network will just, your network will just stop there. It's not going to tell you if it's a planetary nebulae, if it's a remnant supernova, if it's etc., etc. And in this case, it will not work with really large objects. It will work on rather compact objects. So you have a lot of limitation with the number of filters that we have with IPHAS. So I'm going to finish here. So in conclusion, well, IPHAS, it's a new survey, and it's still unveiling new nebulae. We have new planetary nebulae all the time. We have new remnant supernova. There's still a lot to do with IPHAS. And using all those surveys that will help us to solve the bias and the problem when we have to do some really large, some statistical analysis for a determined population. So the detection of the extended nebulae, we use it with bin mosaics that are visually inspected. This is the best way that we've been doing so far. But IPHAS is not alone, so we can be combined with UVEX and with VPHAS+. So VPHAS+ is the same as IPHAS, but in the southern hemisphere. So you have a lot of data. But the number of filters is not that large, so you are restrained here. And in the future, well, all those IPHAS, UVEX, and VPHAS, they are part of EGAPS, the European Galactic Plane Survey. And machine learning, well, that's going to be a tool that can help us to find to complete our detection, to increase our detection rate, to complete the detection of all those objects. But we're seeing there's still a lot of things that have to be solved to improve as much as we can the detection using machine learning. Okay, so thank you very much.
Thank you very much, Laurence. Questions?
Thank you, Laurence. One of the biases you mentioned in obtaining a complete catalog of planetary nebulae is that you will miss those that are highly extincted, in regions highly extincted. But I guess you cannot completely overcome that with an H-alpha survey, which is in the optical. So what type of observation would you suggest to really obtain a complete catalog of galactic planetary nebulae?
You would need to go multi-wavelengths, actually. You will need, if you want to stay in the galactic plane, you would need to have IPHAS combined to something in the near air, the same as IPHAS, but instead of in the optical, you would need to go in the infrared. The thing is that, of course, we are looking for we are all looking for different kind of objects, and you have to take into account the time that you will have to finish the survey, etc., etc. So, and because H-alpha is the line the tracer that you can see in all those objects, so it was easier to go only in the optical. But ideally, you would need different survey with the same depth, actually, with the same resolution. But you would need one in infrared. In the infrared, you would need to combine that with mid-infrared and far-infrared surveys, actually. But for the time being, it was purely optical. UVEX, VFAS also are all optical. Of course, I'm not saying that we're going to find them all, but if we can, the R, for example, is going to magnitude 20. So, and with also the help of the binning, with the mosaic, we will at least try to go as far as we can in the optical, until to say, okay, we cannot do more than that.
Another question is morphological classification. What is the difference between irregular and asymmetric? Sorry? Between irregular and asymmetric?
Asymmetric, basically, it's everything which can be, what do you call that? The point symmetry objects, where you have they're not bipolar in the sense that you have two lobes, but you can find some sort of asymmetry in the sense that you have like point symmetry object that you think that maybe there's precession, etc. So basically everything which might be bipolar but not with the two outflow, the two general outflow as we define category a bipolar. So basically everything which has some sort of symmetry, which was not totally irregular, we put them in asymmetric, actually. That is purely to us. It is.
Yeah, I guess that trying to complete the survey for extincted nebula, you probably have to go to bracket gamma survey, so as to get emission, but without the extinction that we see in the optical.
Hi. How do you plan to process large surveys with terabytes of data?
And from which point of view? For the analysis, the detection of the objects?
The whole process. Detection.
Why we are looking more on the machine learning things, because we won't be able to do that visually for all those objects. It was the first time, so okay, we did it that way, and it works pretty well actually. But machine learning will be the way to go. But it will. I really have to stress the quality of the images to avoid. Well, it depends what you're gonna do, how you're gonna use your images. If you're gonna just use them, you're gonna combine them in a different way. So you really have to have good quality images to do that, to avoid everything which is artifact, because artifacts can be a very large issue with your, in the case you're doing mosaics, for example. If not, even if you're not doing mosaics, it's always good to have nice images. But in that case, yeah, machine learning would be the way to go. So you will need to find, depending on what you're looking, You find a common pattern, and then you train your network, and it will be then easier. But even that, at some point, you will have to do a visual inspection.
Yeah.
Yeah.
The final step.
Final. Yeah.
Use a neural network to detect the artifact.
This is what I said also, that you can also do that. So because the artifact that I show you, they are generally, those are the ones that you always find, the same kind of patterns. So you can also train your neural network to do that, actually.
Thank you, Lorraine, very nice talk. Really enjoy very much. So my question is, what is the proportion of artifacts do you find in comparison with the number of, real objects, real emission objects?
It depends on, really it varies from mosaics to mosaics, because you have mosaics that are composed of frames that were taken with when you have, for example, a very clear sky. All the background are the same, or nearly the same between the H alpha and the R. You have the H alpha minus R. The removal of those mosaics is done nicely without any issue between those two mosaics. So you have mosaics that are clean. So with that, the number of artifacts are really low. And you have places, and for example, maybe the NT center, where you have a bit more artifacts. But really, it depends from one mosaic to one mosaic. But in numbers, yeah, you have much more artifacts than you have objects that you detect. That's why it's going to be interesting to train a neural network to remove all those. And visually, actually, you cannot take the risk, because it can be a compact object that you are having. So we are picking them up, and after that, we are looking and see what they are exactly. Yeah. And you have the edges, the reflection at the edges, but those are easy to discard.
So how close do you think we are of being able to compute a nice PN luminosity function? How close are we, the community, to be able to compute a nice, reliable PN luminosity function?
How close? Yeah. I would say that we are halfway. Because, for example, as I was saying, the anti-center region, it's a region that it's really not well scanned. So, for example, lots of PN are missing there. In the galactic plane, I think that we are getting pretty complete there. So, at least in that side, it's gonna be easier. But I would say halfway, actually, if I can say something like that. Mm-hmm.
It also depends on the total number of planetary nebulae that you estimate, and there are actually other authors that estimate half of the 24,000. So it depends on the models you include to compute the total number of planetary nebulae in the galaxy. I think it is included in that calculation. It includes the star-forming regions in the galaxy in a galactic model, so that's the total current number.
Far, counting the IPHAS objects and the latest one that we have, we're not arriving to 4,000 objects. The lowest estimate of planetary nebulae, the total planetary nebulae, the very lowest one are 16,000. So I think that we are getting, halfway of having a very strong and full luminosity function law of luminosity function for planetary nebulae.
Luminosity function, you need reliable distances to these sources.
A very, very nice talk. I have some questions, but one was already addressed to you about the discrimination between, I'm coming back to the detection side, between the artifacts and what nebula or reflection, these kind of things. But you were also finding objects which were not just planetary nebula. You were also finding supernova remnants and extended H regions, these kind of things. And that's one thing. And the other thing was, IPHAS was to observe the anti-center region. It was mostly unknown, but with distances there is a lot of extinction. There are just 3 channels where not much extinction, but most of them, because you are looking at the plane. So my question was, it was easier for you to find supernova remnants and let's say other nebulae, like World Ring Nebulae, these kind of things, than planetary nebula? Or there was, the same. You don't find these nebula, for instance, extended supernova remnants are the same difficulty to be detected than the other ones.
Detection was, there was not much, it was not more difficult to find planetary nebula supernova. Yeah.
Distribution was not the issue in the detection, actually. The surface brightness distribution or the morphology of the supernova was not the issue, the main issue detected.
Object, those very large, the H2 region supernova remnant, using the 15 pixels binning, there's no problem. Yeah, that was the point.
Step. So, in your opinion, for other surveys outside of the galactic plane would be easier because you expect less stars to be contaminating the. But in your opinion, the best tool to detect very low surface brightness line emission would be a technique based on binning, or so to increase the signal to noise, or.
If it's not binning, any technique that can allow you to increase, to lower your resolution, because you don't really need resolution, except if you, no, because it's for the detection. For the detection, you don't really need resolution. You just need signal. So any techniques, because we talk about wavelets, for example, that can allow you to extract, to increase that signal to noise, will work for all those objects. Because we had some, one of those supernova remnant, we're working on a candidate right now. If you look at it at the nominal resolution, you cannot see it. If you increase at 5 pixels binning, yeah, it starts to appear. At 15, it's bright, let's say. Of course, you have not all the detail, but right now, as I said, you don't really care about the detail. You care about detecting it. So the binning, in that case, the binning is essential to detect those objects. At least this is what we've been doing.
Detection of very compact planetary nebula. How many do you find with this?
The compact. Okay, so the article, the point source. For example, for the point source, it was the article by Vironen et al. In 2009, and the rate of compact was really low, actually. The one that they find in point source. For us, the intermediate one that we called compact, I guess that it would be like, well, just look at the, not saying. Yeah.
It's only to get a guess of what is happening with this kind of, all right. Okay, we can say that, oh yeah, the number of, no, my question is, is very naive, is in the sense that, do you make a cross-matching between this object and Gaia? For example, for parallaxes?
We've not done. But the thing is, for the compact one, if you can see the central star, because you look at the star actually, and a lot of them you don't see the central star is really faint, and we didn't do it yet with the. I know that someone in IPHAS did something like that, the cross-check between the IPHAS, but IPHAS compact source in general, not Planetary Nebulae and Gaia, it seems to me, but we didn't do it for our Planetary Nebulae in particular. This is something that we are looking at. Yeah. Our difficulty is the central star, to detect the central star, because the central star can be really faint and might not be picked up by, or for some reason might not be picked up by Gaia.
Yeah, Gaia is only detecting, a star is also detecting, another kind of objects, so it's possible to find something similar to this.
Working on. But I'm not aware of which one that could be actually. Matching radio survey. I know that there can, but I don't know if it's targeted with the Grand Millimeter Telescope in Mexico. I know that they are doing some observation in the galactic plane, but I don't know if it's targeted or if it's a full radio survey. But with all, well, you have low far as well. But I guess that most of the galactic plane, with all the radio survey that have been done ultimately, you would be able to find a correlation between what we've been doing and those radio survey. But I'm not sure if I'm not aware if all those radio survey are continuous on all the plane. I know that there's projects of having some of them, but I don't know if it has already been done, actually.
Actually, there are some surveys where they are pinpointing new planetary nebulae. No, there are some, I don't remember the name of the survey, but it has some high spatial resolution, relatively high, and there is some population, not very numerous, but a few numbers of planetary nebulae are being detected. Still, those are very highly extincted, and then making new observation to confirm that those are indeed planetary nebulae is difficult.
Data, but I don't remember whether it covered the whole galactic plane.
In more recent survey that probably would go deeper. But yes, for the supernova remnant, we use the NVSS, we use the GBT, well, all the existent one, the already one. But as a new survey that probably will have an increase in sensitivity, this is the one I'm not sure of, if they have some large galactic plane survey.
Okay, so I think it's time to... Here, Laurence is going to be here this week, but also next week too. So if you have any comment or anything you want to comment to her, she's going to be available. Thank you very much for your talk, Laurence.